Hello, this is Mr. Ferrer, and I'm going to continue with the inferential statistics module, kind of looking at the different tests. And this time we're going to be looking at the Wilcoxon test. It is a named test called the Wilcoxon test, but each test has a symbol, and this particular symbol is the T test, and there's actually a couple of T tests. Now, if we look at our flow diagram, of course, we are working along the part of our flow diagram that has now rejected independent groups and moved on to repeated measures. And of course, there's also this matched pairs that we can include. And I explained that in a previous video as to why we would do that. And so therefore, if we see that we are doing repeated measures, there's pretty much a good chance it's going to be the Wilcoxon test. If it is repeated measures, we then can say another reason for doing this test, and this is looking at point 1, is that this time there's a difference between scores, because that's kind of the point of repeated measures. We take the same participants and they do score 1 versus score 2. But of course, there's always a level of measurement, and this particular level of measurement, once again, is called at least ordinal, indicating that it's not nominal data and it's not interval data. Okay, and this is just reinforcing the idea that matched pairs can be used, and that's effectively because each person that is matched is considered to be kind of like one participant, so kind of like they're repeating the test across that. And so here we have a hypothesis looking at a significant difference in the scores in a short-term memory test when it's taken in the morning or in the afternoon. So therefore, what we have is quite clearly, it's not saying that the morning is better or the afternoon is better, so therefore it's non-directional. But we also have this repeated measure. So you either take it, or you take the test in the morning and then you take the test in the afternoon. Hopefully you would also be doing some kind of looking at order effects and kind of changing that around and stuff like that. Maybe think the logic behind this could be that you think that some people think more clearly in the morning or in the afternoon or whatever it could be. But there we have our alternate hypothesis, and this is typically what the data would look like. Okay, what we do notice is that we have to have a full set of data. We can't have anything missing in terms of this, and we have once again the observed value for the T is 26.5, or the calculated value is 26.5. So there's nothing remarkable about looking at a table of data like this. It could just indicate a few things to you. The only thing potentially is that we notice already is that participant number 4 scored the same amount for both tests. And because we're looking for a test of difference, we're going to obviously consider that in a little while. So as I said, each test, it's more about deciding, well, what critical value, how do we find that one critical value that we need in order to do this, okay? So we look at our data like this, and we see that instead of using n equals 12, we're going to have n equals 11, because this wasn't a difference, not a difference, okay? So whether they would have this in the exam or not, I'm not really sure, because I think it's once again a little bit too complicated. But I wanted to kind of show you that, you know, it's about them kind of deciding, do you know enough in order for them to award you the marks, okay? So the first things we have to do is we have to know that n equals 11. We have already decided that we tested 5%. And we're told that it was two-tail, okay? So therefore we look at a critical value table, and we see quite clearly that there's only one value, and that is that is t equals 10. That is the critical value, okay? Remember, when you quote or you say a critical value, you give all the details that you know. So for example, it's only that 10 because n equals 11 and it's two-tailed and it's at 5%, okay? In this particular case, we can ask the question, says observed value of 26.5 must be equal to or less than the critical value of 10, must be equal to or less than, oh, that doesn't make any sense, so therefore it's insignificant. And I'm kind of rushing through this because by now I'm hoping that all of this is fairly straightforward, okay? it's always good for you to write these types of things down. So the observed value is greater than the critical value. So therefore, it hasn't met the condition. So therefore, we accept the null hypothesis. I would say the only reason I'm doing this is because I do know that some people do say accept rather than reject, okay? I would personally prefer you to say we therefore reject the hypothesis and conclude that there's no difference in the scores on the short-term memory test when taken in the morning or the afternoon. Okay, so really quite an interesting idea to look at, but of course there's no evidence to support it. Okay, so using this particular table, we can do the same type of thing. So n equals 6, it's directional, observed value 3. Directional, n equals 6, so that is 2. It says that the observed value must be equal to or less than the critical value, so therefore we would reject that because it's not less than or equal to, and so forth and so on. So please continue to have a look as to whether you can do this. So n equals 13, non-directional, 13. So we've got 17 there, okay, 17. So therefore this one is significant because it says it has to be less than or equal to. Then we have one-tailed 12, 10. Okay, so one-tailed 10 is 11. Okay, so therefore insignificant. And then we have another one of n equals 11, so that's 10, and therefore insignificant as well. Okay, so please just kind of practice that. Practice looking at a critical value table like this, making sure that you can figure out exactly where things are and that you're able to kind of follow the instructions and decide whether it's significant or not. Also then decide whether you reject or accept your hypotheses. Now, this is not a particular question that they seem to like. I don't know why they don't seem to like it as much as the Mann Whitney. But of course, this will be one that they're asking you for significance because the table is easy to kind of print and things like that. So therefore, the Wilcoxon, nice little simple test, and I hope by now things are becoming a little bit quite straightforward for you. So therefore, we move on to the more complicated version of this. And this time, of course, it would be called the related t-test. I told you there's a couple of t-tests here. And of course, it's related because if I'm either matching or if I'm going from one test to the other, of course, one value is equal to another. So one person's score is related to the other person's score. And we see that we have the same reason 1, okay, testing for a difference of scores. We have the same reason 3, it's repeated measures. But of course, now we have interval data, and of course, we have this idea about the normal distribution as well. And this is a typical example of this. Okay, it says there's a reduction in heart rate activity when comparing heart rate before and after cognitive behavioral therapy. Okay, so the reason that it's going to be interval data, of course, is the heart rate activity is measured in beats per minute. So therefore, it's a standardized kind of interval type of data, and we see that they are telling us what direction it's going to be, and as such, we have the same kind of situation as we've had before with your interval data and kind of knowing that before and after cognitive behavioral therapy that things are going to change. Now, in this particular case, as I said, it's the same as Wilcoxon. We don't do anything different. But this time we find that actually the degrees of freedom are going to be slightly different. It says that degrees of freedom equals n minus 1. And I suppose the way I've always tried to remember this is, of course, there's one group. And of course, one group means that there's 1 degree, that's the minus 1, of change. And so therefore, that's why we minus 1. Remember when they had 2 groups, we did minus 2. And I suppose maybe it's something a bit like that kind of helps us with it. But once again, I would still say that we are looking for a situation where they'll give you either the degrees of freedom or they will tell you what to do in terms of substituting it into a formula. Now, ultimately, I don't feel that this is overly complicated. I think the biggest task is choosing the correct test. I think the next biggest task is understanding kind of how do you take that statement at the bottom and how do you work with that in order to know what the observed value is and what the critical value is, and then the decision whether it's insignificant or not. I think it's obviously more important for you to understand kind of where we're putting hypotheses and rejecting and accepting and stuff like that. So I hope that it is going well for you. We've got one more kind of test to do after this, and there we have. We've actually done the inferential tests. I'm really proud of the progress we've made so far. So I'm going to sign out. I hope you to see you soon, and take care. Bye.